Hi, welcome back from spring break. Hopefully you didn't get sick like I did. I am going to walk through today's class via this video. I want to start by pointing to our morning start page that has a week 9. So we're in week 9 now, to-do list. And if you click on that, it'll take you to Brightspace and it'll just review the stuff that's already on there. The soft deadline for the smart book reading on chapter 6 was last night, so hopefully you've completed that and have reviewed everything regarding hypothesis testing that's in that chapter. The hard deadline is tonight, so if you didn't realize you had to do it last night, you still can do it for tonight. And the main thing that you want to start working on is the task 2, part 2, exploratory data analysis assignment. This is Excel assignment number 6. And I want to make sure that you understand that this is part of the work that we started in class on Thursday. If you come down in the assignment instructions, it'll have a link to the data that you want to be using. And it talks about how we want to use the questions from Catherine Hill to begin to answer them using the data. And we don't really know how we're going to answer them. Her questions were sort of vague, so we are going to explore the data. We're looking for signals. We're looking for things that are related. And I would like to point you to, there's the exploratory data class example from last semester and a video showing how I started that. And that hopefully will get you started. You can't use the same exploratory data, postulates. You have to come up with your own. And these are like questions or hypotheses or postulates, which is a statement of something you think is true. And as I told you in class, if you do a exploratory data analysis to try and determine if your postulate is true or false, and it turns out to be false, there's nothing wrong with that. That is actual information that is valuable. It would end up going in an appendix in the technical report. For right now, though, I'm also using this exercise to strengthen your tool chest of making visualizations and knowing when to make what kind of visualization. So what you're going to want to do is do a minimum of 8 postulates, and you're going to want to have at least one of each of the different types of visualizations that we went over in chapter 4. And there's videos on Brightspace that are chaptered by the type of visualization, so you can make sure you look at that to get the information and a step through and a guide on how to do each type of visualization. You want to end up having 2 positive ones for each data set. So one for the full data set and one for the millennial subset. You're going to need this to continue to do work in providing answers to Catherine Hill. And let's go back. So that is due Monday. And I recommend you get started on it so you have time to figure out how to do all the different ones. In the video that's in here, where'd it go? In the video that's in here, so here you see it says Excel assignment number 6. This is where it starts. So below that, I do refer to other videos. So kind of guides you through setting it up. Well, and if you were in class on Thursday before, you know the way we were thinking about this. Okay. I also want to draw your attention. I want to open this up the way you see it on your end. So if you go to your coursework, come on down in the exam 2 material, you should see a folder called Statistics 1 Additional Background. I'm not going to go through this. This is stuff from when I taught BAI 210. But I am providing it to you so you can go through it if you feel you need more background on some of the topics we're going to be touching on. I'm happy to meet with you during my student support hours and coach you through understanding what you need. Remember, I'm your cognitive coach. All right, so we're going to be in exam 2, chapter 6. We're going to start with this hypothesis testing intro. And I realized that in order to be in my class, you have passed a Statistics 1 course in some form. And I also know that a lot of you may have had somewhat of a challenge dealing with the hypothesis testing material. So I'm going to attempt to somewhat reteach that. Okay. So I'm going to start today by talking about the general setup and logic. So the nature of hypothesis testing is you want to start with a question related to a mean value. That's one way to think about it. Another way is you can think of it as starting with a question related to a proportion, and that would apply to categorical variables. But just to keep our thinking of this a little cleaner, let's just start with a mean value. So for example, is the mean weight of chips in a bag not equal to the advertised 454 grams? Or has the average miles a car lasts before it dies increased since the 2010 average of 185,000? Notice that in both these questions, we're referring to a value of the average. The hypothesis statement, the hypothesis will be a statement that something is true. And there's two types of hypotheses. One is the null hypothesis. And we give that the notation H sub naught. And this is the hypothesis that is going to be tested. It's written as an inequality, as an equality or an inequality, but it always contains the equal sign. So greater than or equal to for the inequality or less than or equal to. The alternative, and this is where hypothesis testing throws a lot of people, and you just have to wrap your brain around this and get it. The alternative is what we call the research hypothesis. This is really where your question is. So the idea with hypothesis testing is is that these are exact opposites of each other. And you're indirectly going to want to try to prove the alternative. You can't directly do that. So you indirectly do it by rejecting its opposite or showing the data gives us confidence in rejecting the opposite. So it's referred to as the alternative. And our strategy in hypothesis testing is all about trying to show something is true by rejecting its opposite so that we can accept it. Okay, so the first thing is when you're going to do a hypothesis test is you have to come up with the null and alternative hypothesis. And as I told you before, the null hypothesis contains equality. So it's either equal to, less than or equal to, or greater than or equal to. Here's some examples. The alternative is kind of where you put what you believe is true, or what you're concerned about, or what you want to test is true. And so for our course, and since we're trying to use this tool in the context of business analytics decision making, and we're trying to give organic food superstores suggestions to answer the questions, we want them to be quantitative. The alternative, and we'll see this in some examples, is where you're going to put we'll start with writing it in English, but in interpretation for your exploratory data analysis from a positive postulate. So if you see something in a exploratory data analysis, this is sample data. I believe we have 184 records. We're going to assume Catherine Hill and Organic Food Supersource have millions of customers. So we can't say anything with confidence about all of their millions of customers unless we use proper statistical techniques to use our sample data to guide us. And that's why we're going down this whole statistical path. So step one, you come up with the alternative hypothesis. So again, this for us is going to be coming out of a positive exploratory data analysis where you actually saw a signal. This is what you believe to be true, what you're concerned about, or what you want to test. So here are a few examples, and in some ways, I'm starting with the mathematically or statistically most simple, but in many ways the least useful, because often our questions are going to be more useful if we want to know about the difference of the means from two different subgroups. That's where we're heading, but let's just start with one mean from one group and asking, is it different than some value? Is it less than some value? Or is it greater than some value? So notice that the alternative never has equality. So we want to know is, in the alternative, is this population, notice this is now, we're going to be trying to say something about the whole population. That's why we're using the statistical tool. It's very powerful for this. Is based on our sample mean. We're trying to say something about the population mean mu. That's why it has the Greek letter. And that's the big unknown. We don't know, we can't get our hand on millions of customers. Assume that is true. Okay. To know, or millions or whatever. Anyway, so in this case, what we're saying is that population average is not equal to 37. All right. And this 37 here is the value that we're going to give a general notation for called the mu naught. So it's got that little knot there, which means it's just a specific, which means you're referring to an actual number, and that's, in this case, it's 37. Now, remember I told you the null hypothesis, mathematical opposite. So if something does not equal 37, the mathematical opposite is it does. Right. The next type of alternative is you could say, well, I don't think, based on what I saw in my sample data on my exploratory data analysis, let's say, I don't think that and by the way, included in here would be your summary statistics. So let's say you look at your sample mean. I don't know what 678 is. Maybe it's how much you spent in 2021. And you see that the average, our X bar, right, coming from our sample data is less than 678. So then you'd say, okay, I'm guessing that based on our sample data, that the overall average spending is actually less than 678. So this is going to force the mathematical opposite. The mathematical opposite is that the overall population is greater than or equal to, because you got to include that equal to, and it's always in the null. Or let's say now we're talking about number of orders placed, and you look at the sample data and you notice in the summary statistics that the average number of orders placed is actually like 50 something. You say, or last year the marketing team was using this 23.5 to guide them, and you're like, no, I think it's actually more. So this is your alternative. And that's going to force your null to be the mathematical opposite. So if this is greater than, it's going to flip to less than, and you can add the equal sign. Okay. So let's just go through this example. Apologies, or maybe not apologies, but for those of you who had me for my EAI 210, this is the same example we used in that course. So a snack food company makes bags of chips with 454 grams on average. And They could get in trouble if they don't put enough, and they could get in, and then they're wasting product if they put too much. So they have an quality assurance people. Most companies will have this. They are going to periodically check if the big bagging machinery needs to be recalibrated. They want to decide this based on the results of a hypothesis test on a sample. So that's the key. The sample is a smaller number, right? And they're trying to say something about mu, which is the average for all the chips that bagging machinery would bag. So it's the mean weight of a bag of chips, any of all bags of chips made by this bagging machinery at this point in time. So um, they're concerned about it not being 454, right? So make sure you can follow the logic here, and you would be able to do this yourself. So their concern, because they're the quality assurance people, is that it's not equal to that. So their concern is actually the alternative. And then the mathematical opposite is that it's equal to the stated printed on the bag, 454 grams. So we're going to start by assuming that the null is true. The equal part, in this case, that mu equals mu naught. And that there's a normal distribution, or for us, we'll generally be using the student's t distribution around this hypothesized value, mu naught. Okay. So we assume it's true, so that's why the mu naught is where the average is for the distribution. And if you don't remember about normal distributions and adding standard deviations and the empirical rule and all of that, please review that in the Stats 1 folder. Right, so we're going to give, if we're given a confidence level and with a significance level alpha, we can build a confidence interval around this mu naught. And unfortunately, this got cut off. This should have been a mu naught right here. I can't draw this stupid thing. Okay, mu naught. So what we're going to say, right, just to remind you about doing confidence intervals, is we're going to say the significance level is how much error we're willing to be wrong, the probability we're wrong. Alpha is usually a small number. When you build a confidence interval around the mu naught, which is what we're assuming is true, we're going to take how much error we're willing to live with, divide it in half, and put it in each tail. All right. So we want to figure out the width of this confidence interval right here, right? We want to know what these values are on the x-axis. And the first one is going to be and building a confidence interval, and how we get these formulas is part of the slide deck in the Stats 1 material. But basically, if it's a normal distribution, we will use a z. If it's a student's t distribution, we would use the student's t for how much error or how much probability is in the tail. And this t value or z value is multiplied by the standard error. So the standard error is the population variance divided by the square root of n. And then we'll talk about what happens when you don't know sigma. At this point, don't worry about exactly understanding this formula for the confidence interval. You can go back and fill that in later. But right now, I want you to focus on the logic of hypothesis testing. So in this example, we've set up our alternative, pretend you're part of this quality assurance group, and you want to make sure, you want to test that what happens is it possible not equal to 454. And we're going to test this at a significance level of 2%. And if you remember, you subtract the alpha from 100 to get the confidence level. So if alpha is 10%, the confidence is 100 minus 10 or 90. If the alpha is 5, it's 100 minus 5 or 95%. And we're going to put alpha over 2 in each tail. So we want to get the z-score for a 0.01 probability in the tail. And that comes out to a 2.326. And so we're going to add 3.26 times the standard error, and we're going to subtract the 2.326 times the standard error. So I'm going to open up this question. It'll be available until Wednesday night. Match the null hypothesis on the right with the corresponding alternative hypothesis on the left. I think I can show that to you. So you're just going to match these up, make sure you understand what we did. Okay. So the next big step in the logic is, okay, if the population mean is equal to that number, mu naught, there's a probability of alpha of getting a sample mean from our sample outside of that interval, right? So that's what you want to understand, that this is probability of alpha of getting a sample that's weird, and alpha is really small. So if you get a sample mean and it is really different than what you thought it was supposed to be, the probability of seeing that is alpha. Okay, that's the whole theory that this builds on. All right, so let's go through this a little bit more. Okay, so we start by assuming that the null is true, right? Remember, we're trying to actually secretly, right in the back, or strategies that we're hoping to prove it's false, but we proceed as if it's true with the hope that it leads us to something that is very highly unlikely. All right, so we're going to assume it's true. We assume there's a normal distribution, or student's t is more likely what we're going to be working with. Around the mu naught, we know that the sample mean is distributed around the population mean, and that the sample mean, recall again, this is in the background material, that the standard deviation of the sample mean is referred to as the standard error, which is sigma divided by the square root of n being the sample size. Right, so we want to know if we can set up the probability. So we set up an interval. Right? What's the probability that the sample mean is less than x1 bar? So this should have a little line right here. You can see it up here. The font here is sort of messed up. Right. So I've kind of shaded this in. So what's the probability is what we refer to as the p-value, that our sample mean is less than some x bar 1. Okay, if the truth is that the population mean is equal to that number, for us in the bagging example was 454. Okay, so now the next step is on the other side. So we now look at a sample mean 2 number, and the probability, or the p-value, is what's the probability that the sample mean is greater than x bar 2 if the truth is that the population mean is mu naught. And just to remind you, and then just a little bit chopped off here, so let me see if I can pull it up this way. So here's a slide, so you can see where it came from. Just make sure you It's not chopped off there. 1 minus x bar. So if you recall, again, this is in the background material. If you want to get the probability of something to the right of a number, both Excel and your tables always give you the probability to the left, but the area under the whole curve is 1. So we just say, oh, if you want the area to the right, it's just 1 minus the area to the left, and that leaves the remainder, which is what we are looking for here. So what I'm trying to point out is depending on where your sample mean is, when you have equality, you are going to either be trying to determine a probability in the upper tail or the lower tail. So let me go back to the top hat presentation. Okay. So we're going now, again, reviewing back where we were. So we have the probability of alpha of getting a sample mean outside of this interval if this was actually true. So if the bagging machine, think of the chip bagging machine, is actually working just fine, and we go and we get a sample, there's only an alpha, and let's say alpha is like 2% probability of getting a sample mean that's outside that interval. So we kind of want to figure out where that interval is, and we want to know what's the probability of getting the mean that we got. And I'm sorry that this keeps getting cut off. So we're down here. All right, so if you're below, if you have a value of your sample mean that's on the lower tail, that's the terminology that's used. So there's this cutoff value. We want to know that probability, and that's referred to as the p-value. So we're going to compare the p-value, and we want to know if it's less than or equal to the area in the tail, then what we're saying is the probability of seeing the average found is less likely than what we determine by the significance level, which means that's how much we were willing to be wrong. So we were willing to be wrong 2% of the time, and if the probability of what we're seeing is even less than that, then it's very likely that if the truth is that the population mean, now remember, this is kind of going in reverse logic. What we're saying is if it's true that this u0 is where the mean is, then getting our sample mean is not likely. Okay. So if mu equals mu0 is a true statement and x bar is normally distributed, then the probability of randomly choosing a sample whose sample mean is less than that number, the mu0, minus the z-score for the with an alpha over 2 for the tail times the standard error is alpha over 2. And I believe this will be a true false. So you can answer that if you want right now. Okay, so continuing to build the basic logic. So if the p-value is less than or equal to the area in the tail, remember the p-value is the area given the data. So the p-value is the probability that our sample mean would be less than or equal to this x bar 1 if the truth is that the bagging machine is doing the average we think it is on for all chips that are bagged. Okay, so that was the conclusion. This is where we are at the last slide. Now the decision is, and this is where we pull the rug out from under the approach. I mean, this is kind of like the strategy if you were a lawyer, is instead of saying, oh, okay, that's just not likely, what we say is, okay, you know what? Actually, we just don't believe the hypothesis. We say this is so unlikely that we just don't believe that the null is true. So we reject it. And then this is the path to accepting the alternative. Okay? So that's the big logic of it. You assume something to be true and you are follow the logic. If it were true, what it would mean. And then you show that your actual data is so unlikely that you believe it is evidence to prove that your original hypothesis is false. So you reject it and accept the opposite. Okay. Alternative result. You compare the p-value, right? The probability in the corresponding tail. Again, this is if you had a two-tail test. And if it's greater than the area in the tail, this means the probability of seeing the average you found is more likely than what is determined by the significance level. And you may be like saying, well, that's not really plain English. So let me try to make it even more plain. What it's saying is you got an average in your sample, and it may be slightly less than the population mean you think is true in your null, but the probability of seeing that is greater than the error you are willing to have. So you were willing to have, let's say, 2%, and you find out that this probability for the sample you got is like, I don't know, 14% probability you'd see that. And you're like, okay, well, it's within my margin of error. Right. So in that case, if the p-value is greater than that area in the tail, then the conclusion is that if this is true, this is likely. And the word likely is because it's within our margin of error. All right. So then your decision is you're going to believe it's true. So you do not reject it. And you do not accept the alternative. Okay. Notice that we haven't proven that it's true. We've just failed to prove it's false. So we cannot accept the null. We just fail to reject the null. Once a specific sample is obtained and x bar 1 is calculated, then the probability that any sample mean is less than that number under the condition that mu equals mu naught is called. And then what you want to know is it the p-value, the confidence level, or the significance level. So let's go through the steps again. We're going to set up the hypothesis test, get some sample data. SRS, if you guys recall, is a simple random sample, and get the average. We're going to call it x bar 1. We're going to compare the p-value. So this x bar 1 is going to go, so you put it on a number line. You got some mu naught number that's coming from your null hypothesis. You graph this somewhere on your number line. Let's say it's here. And you want to figure out if there's a normal distribution around mu naught. Sorry, that was supposed to be right there. What's the probability in the tail of you seeing this or any value greater than it? Okay, if that, and that's called the p-value, right? So that area in there, that's the p-value. And if that is less than what you are likely to accept as a margin of error, then you're going to reject the null and accept the alternative. If it's greater than, if the p-value is greater than the area in the tail that you were willing to have as a margin of error, then there's no reason to not believe the null is false. So you do not reject it. So we're going to set up the hypothesis, get the sample data, switch over to a standardized normal distribution. This is just to help the math be clear. So we're going to need to get what's called a test statistic. So I've kind of glossed over this x bar 1. So now I'm going to come back and talk about the basic logic of the hypothesis testing. So in order to make the math cleaner and make us enable us to have a tool that we can apply using Excel, for example, or generally over and over, because you could have a normal distribution around, an infinite number of sample means. We're going to standardize it by switching everything over to the standardized normal distribution. And that means we are going to kind of recenter and rescale our X, our sample mean that we got. So our X bar 1 in this case. And by getting the z-score, so this is getting the z-score, we're calling this the test statistic. And that means we now are centered at 0. So again, if you need to remind yourself about this procedure of converting everything to a standard normal, no matter what you have as your hypothesized population mean, how to get the z-score, please refer to the background material from a 210 course. But the bottom line is you have to convert it over to a standardized normal distribution that would have a 0. And the big benefit also is, if we recall, with a standardized normal distribution, not only is the mean 0, but the standard deviation is 1. So when we build out and we're going to test to find the location of these values, we are multiplying by a standard error of 1, so that all we need to do is determine the z-score associated with the alpha over 2 tail probability. All right, so we can convert the hypothesis test to the standardized version. And I'm putting a u sub z here to be clear. So we're saying u sub z is equal to 0. It's not equal to 0. Remember, u sub z is the z-score version. So we centered on mu naught and we divided by the standard error. So now the logic is the same of everything we've already gone over, but the notation is cleaner. So we compare the p-value based to the area in the tail that's based on alpha. And it's the same thing as before. If the area in the tail, based on our z-score from our sample data, is less than the area that we were willing to live with as the margin of error, so it's even less likely to occur, then we reject the null and accept the alternative. But if the area based on our sample data of how likely it is to see what we're seeing or a value less is greater than our margin of error, there's no reason to not believe it's true. And so we do not reject the null. Okay, so now that we've talked about all this theory, let's try to make it a little more concrete by working through an example, the one that we already started about the quality assurance group checking out the chip bagging machinery to see if it needed to be calibrated. The bags that the chips are going into claim there's 454 grams of chips in the bag, and the quality assurance people need to check if that has gone off, right? So we are going to check in this rewritten standardized wet version by getting the z-score is if the mean is, the standardized mean is equal to the 454 average, right? Which is, when we do the z-score, it turns out to be a 0. And the alternative is that it's not equal to that. Okay. And we already, so this is all where we were before, previous slides. We talked about doing this with a margin of significance level of, so how much error we're willing to live with, of 2%, which we're going to split into each tail. And from that, we arrive at the z-score associated with the alpha over 2, or 1% of probability, is a standard z of 2.326. And so all that's saying is the probability of any value z being less than negative 2.326 is 1%. All right, so now what do we do? If you were the quality assurance people, they're going to get a sample of 60 bags. and they're going to precisely measure everyone and then get the average of those 60. So this will be a column of data in an Excel sheet. And they find that the average is 452.5 grams. So they want to know, how likely are you to get an average from 60 bags of 452.5 grams if the machine actually is at 454 on average? And maybe they just got a sample, the 60 just happened to get a few light ones and drew the average down. So the first thing is you want to get a test statistic. So this is just the z-score for that for that sample mean. So on a couple slides ago, I reminded you the test statistic is the sample mean, so x bar 1 minus the number here on the right of the null hypothesis, and it's going to be 0 in this case. Sorry, it's going to be 454. Sorry, I have a little bit of a fever. Okay, divided by the standard error. So let's just quickly remind ourselves how we would do this in Excel. So let's just, first of all, I just put in mu naught is the 454. That's what we're assuming is the average. And so X bar is the 452, but that's our sample mean. And sigma is the assumed, we know the population standard deviation of 3 grams and the sample size is 60. So we're going to say X bar minus mu naught in the numerator with parentheses around it, divided by sigma, and that is divided by, in the denominator, the square root of the sample size. And putting that all together, we get a negative 3.87 if we round to 2 decimals. Okay, so once we have that, we're going to want to get the p-value that's associated with that test statistic. So now here's our negative 3.87. I recommend you do a little rough drafts, normal distribution, and go ahead and plot your test statistics so you're really clear what side of the 0 you're on and what you're doing. We want to get the area under the curve up in that tail up to the negative 3.87. All right, and that is what we call the p-value. That probability is the p-value. It's the probability that any standardized sample mean would be less than negative 3.87 if the truth is that the mean is 0. So in Excel, this is done with a function called norm S for the standard normal distribution. We put in the z, so we're putting in that value, the negative 3.87, and then we say cumulative is true because this function can give us this little height, the y coordinate, but we don't want that. We actually want the area under the curve. So we say cumulative is true. So let's pop over to Excel. Make sure you are able to do that. So the p-value here would equal norm S distribution, and it wants the z. So I'm going to click on the z, and then I'm going to put a comma, and then it wants to know, do I want cumulative or not? I think if I back up, it'll give it, yeah. So I want cumulative distribution. So I'll say true. And from that, I get 5.37556e to the negative 0.05. So I just want to make sure you can read the scientific notation because this throws a lot of people off. This is actually what it's trying to say is that this is equal to 5.37556 times 10 raised to the negative 5. Right? So that's what that means. And that's how Excel is expressing that. So if you recall, what that equals to is that we're going to put because it's a -5, we're going to have 5 zeros. We're going to move this decimal that's after the 5. 5, this could be a 7. We're going to move it -5 spaces to the left. So 1, 2, 3, 4, 5, 5, 3, 7, 5, 5, 6 is the actual number. Okay. So that's what the probability of getting a sample with 452.5 grams with a sample of 60, if the truth is that the average in general is 454 grams. So I just rewrote that here. So this is that probability. That probability is so small, it's extremely unlikely, not likely at all. Okay. So the decision based on the p-value versus the area in the tail, which we got from alpha, remember that's how much margin of error we're willing to live with. It's so much less. I mean, it is so unlikely that for us to see this. So that's kind of like, it's really, really hard to get a number this far away from the 0 if the mean really is 0, the standardized mean. So we're going to reject the null. We're going to accept the alternative. And the alternative up here was that the mu sub z does not equal 0, but that actually can be translated back into the original units, which from a few slides ago was that the average is not equal to 454 grams. So the interpretation or the decision, and you always want to do this at the end of a hypothesis test, is that it's time to recalibrate the bagging machine, since to a 2% significance level, it is not bagging chips to the advertised 454 grams. Okay. So let's just go over the steps again. Set up the hypothesis test, get the sample data, do the calculations on the data by getting a test statistic. Decide if the data allows you to reject the null or not reject the null. If you can reject the null, then you accept the alternative. If you cannot reject the null, then what you would say is that the data does not support rejecting the null in favor of the alternative. No, you can never accept the null. We're not accepting a null, we're just failing to reject it. We're going to decide setting up the precise criteria for rejecting the null by calculating a test statistic. This is like a z-score, and we use it to decide if it's likely the null hypothesis is false. All right, so here's another question. Match the decision on the right with the hypothesis test results on the left. So if you're going to decide what to do, and you can review the slides, the p-value is greater than the area and the tails based on alpha, or if the p-value is less than or equal to the area and the tails based on alpha. So again, a little bit of a review of vocabulary. So the null hypothesis is a hypothesis to be tested. We use the symbol H sub naught to represent the null hypothesis. The alternative hypothesis is really what we're trying to see if it's true. It's also called the research hypothesis. It is the mathematical opposite of the null, and it's given the symbol H sub A. The hypothesis test is the problem. The problem in a hypothesis test is to decide whether the null hypothesis should be rejected or not rejected. If it's rejected, then we accept the alternative. That's the only path to making a case for what you saw in the data from your exploratory data analysis postulate. Okay. You can be making some errors. I want to review the whole concept of errors in hypothesis testing. So first one is, let's say you have a true mu, for example, with the weight of the bags of the chips is 454, but our sample had 380. And that was so far away from the 454 when we did the hypothesis test, we ended up rejecting the null. So the null, which was at mu equals 54, was true. Okay. So, but we rejected it. So that was a type 1 error. And the probability of doing that is alpha. Remember, this is what I keep telling you. This is the probability of a type 1 error is like our margin of error, how much we're willing to be wrong. And do not reject H naught has a probability. So you're going to only have two options and you're going to have to choose one or the other. So that means by just plain logic, yeah, 100% of the time you got to either reject or not reject at all. So this has a probability of doing this of alpha. This has a probability of 1 minus alpha, which would mean you had made the correct decision. In this case, in this hypothetical, it's a hypothetical situation. Right. So now in another hypothetical situation, it turns out the true mu was 654 grams. Right. But we didn't know what the true mu is, right? We are assuming it's 454. And we get a sample of 460. And 460, so right, our null was that mu was 454, and it was false because the truth, if we were God and we could somehow really know, it was sort of 654. We don't know that. All null is that it was 454. We get a number close enough, we don't reject the null. All right. So this is a situation where the truth is that it was false. And we ended up not rejecting it. And that's called a type 2 error. So that is failure to reject the null when it is false. And that probability is given the notation beta. And then again, because one or the other is going to happen, you're either going to reject or not reject, the probability of making the correct decision is going to be 1 minus beta. So there's two types of error. A type 1 error, rejecting the null when it was true. That is the type 1 error, rejecting the null when it was true, and that's in this square here. That has a probability of alpha. We call that the significance level. The type 2 error is not rejecting the null when actually it was false. And that's probability of a type 2 error, which we call beta. So on the flip side are the two correct decisions. You do not reject the null, and the null was actually true. So that has a probability 1 minus alpha, which we call the confidence level. On the other side, if you reject the null and the null was actually false, that's what you want to do, that probability is 1 minus beta, and that's called the power of your test. Ideally, we want alpha and beta both to be as small as possible, right? We want our confidence level, which is 1 minus alpha, to be as big as possible, and our beta to be, and power is 1 minus beta, so we want that to be as small as possible. But there's a relationship between them. So for a fixed sample size, the smaller we specify the significance level, alpha, so usually we want alpha as small as possible, the larger will be the probability of a beta, a probability beta of not rejecting a false null hypothesis. So you got to decide which is worse. Pick your poison. So if alpha is 0.05, the chance of rejecting a true null is small. We usually go with a small alpha. So if we do reject the null, we can be reasonably confident that H naught was actually false. And that's, sorry, it's kind of hidden in there. Let me grab it real quick. All right, so if alpha is small, all right, and we do not reject the null, we can be reasonably confident, sorry, and we do reject the null, we can be reasonably confident that the null actually was false. And when we accept the alternative, it's true. That's usually the path we take. What people will do in real life is try to bring them both down at the same time by making the sample size bigger. That's the only other variable that we can really affect here. So one way to increase the power and raise the confidence level is to increase the sample size. So the bigger you make the sample size, I might have misspoke. You want to make the sample size as big as possible. It'll bring them both down. It's the only thing that works. The problem with that is that that's usually expensive. It's usually expensive to increase your sample size. So a lot of times the sample size in a sample in the real world is determined by a conversation or a discussion of the risk of having alpha small and beta not as small. And so the power of the test is usually the driver, one of the drivers, and what's the maximum sample size that a company can afford. Okay. Suppose that a hypothesis is conducted at a small significance level. If the null hypothesis is rejected, we conclude that the data provides sufficient evidence to support the alternative. If the null hypothesis is not rejected, we conclude that the data do not provide sufficient evidence to support the alternative. But we usually don't know beta, the probability of not rejecting a false null hypothesis. In other words, the probability of a type 2 error is unknown. So because of that, that's another kind of explanation is why we never accept the null. So we could think of it that H naught gets the benefit of the doubt and the alternative has the burden of proof. Match the terminology on the left with its definition on the right. So you want to make sure, oops, what happened? You want to make sure you know what a type 1 error is, what a confidence level is, what power is, and what a type 2 error is. So let's revisit. Now that we've kind of gone through a basic example, we're going to go through what do we do to set up a hypothesis test, because they're not always going to be set up the way our first example was. The main question that you want to start with is you're going to determine if it's a left-tailed, a right-tailed, or a two-tailed test, and you do this using the alternative hypothesis. So I'm focusing on the alternative. Remember, this is where your real question is. So if your alternative is if your mu is actually less than some value, we call this a left-tailed test. And you can just think of this as being an arrow and a point. Which direction is this arrow pointing? So it's pointing to the left. I should have put this as an asterisk. I didn't mean to make that an arrow. So this is where you look, and then this is your arrow that tells you this is pointing to the left. It's a left-tailed test. If you want to know if your actual average is greater than some number, it's a right-tailed test. So that's in your alternative. If it's not equal to, this is like the example that we already went through. It was a two-tailed test. Let x be the number of miles a car lasts before it dies, and mu is the average considering all cars. The following hypothesis test has been proposed. So the question is the true average decreased since the 2010 average of 185,000? So we put that in as our alternative, and we use that to determine the null, which is the mathematical opposite, is if mu is greater than or equal to 105K. So based on what I just went over in the last slide, is this a left-tailed test, a right-tailed test, or a two-tailed test? In all hypothesis tests, like I said, we're going to determine that. I think this slide might have got messed up. Build this. Yes, okay. So equality, as I said, is always in the null hypothesis. It is the lower bound of the left tail test or the upper bound of a right tail test that would make the null true. We use this to build the logic of hypothesis testing. So We are going to convert everything over to a z-score, and we use the, we want to look at the mu sub z and see if it's less than or equal to or z naught for a left tail test. For a right tail test, we're looking at the area in the upper tail. And in a two-tail test, we're going to look at the area in both tails. So you're going to figure out where your test statistic lies, and you get that area, and then you need to compare that. You need to multiply it by 2 because we're going to compare that to the alpha from a two-tail test. All right, so that was sort of the general setup and logic. And I'm going to continue to talk about tests for one mean. We sort of did one example already, which was a rare example where we knew what the population standard deviation or sigma was. That is very rare, very unlikely. So we're going to continue to talk about tests for one mean in a more realistic scenario. And then we'll go through and we're going to learn about difference between two means, which is much more common. And then we're going to switch over to categorical variables and talk about tests for one proportion, and then the test for a difference between two proportions. And these, the two I've checked, are the ones that are going to be more useful to us in the real world and also in our class project when we're trying to help Catherine Hill with her questions. All right. In all of these different tests, they all follow the same general framework. And that is that you have to first calculate a test statistic. And the test statistic is always the observed value minus the expected value that comes from the null hypothesis divided by the standard error. The standard error is usually what gets complicated depending on what test you're running. And what test you're running will become obvious based on what you know about your data. So we're going to start with a one sample mean. So you take a sample from your data. You have a sample. You already do have a sample, and you're going to get a mean. And we already calculate means for every variable. And then you're going to subtract off what your null hypothesis for that value is, and we're going to divide by the standard error. Now there's two scenarios. We either know sigma or we don't. We usually don't. So we usually don't know sigma. If we know sigma, the test statistic is just the observed sample mean minus the expected from the null hypothesis divided by the standard error, which is sigma divided by the square root of it. If we don't know sigma, we're going to use the student t-distribution with the degrees of freedom of n minus 1. Remember, n is your sample size, and it's almost the identical formula. The only difference is we don't know sigma, so we're going to use the sample standard deviation in this formula to get our test statistic. In all of the hypothesis tests, we're going to compare the p-value to the significance level alpha. This is the actual test used to decide if you reject the null hypothesis or not. So if the p-value, so here in the green shading is a left tail test, and the p-value in this, this has nothing to do with left tail, this is just an example. In this case, the p-value is less than the alpha. So that means the probability of what we're seeing is even less than the error we were willing to live with. So it's really unlikely to be true. So we reject the null and accept the alternative. We would say that this test is statistically significant. In the other case, and I'm just showing this on a right-tailed test, we find a p-value. If it happens to be less than, a greater area, so the pink here is greater than the area, in the green shading under the curve. If it's greater, we do not reject the null. The test is not statistically significant. We would say the data does not support rejecting the null hypothesis. Right. If it's a two-tailed test, we are going to take the p-value and we're going to determine if we Our p-value is going to be the area under the tail. And let's say our test statistic is on the left side of 0. We're going to get that area and multiply it by 2 and compare that to the alpha. Or you can compare the side you're on to alpha divided by 2. Whichever way makes sense to you. Come see me if you need to talk about that more. All right. The general steps for a p-value approach to hypothesis testing. We're going to state the null and alternative. Remember, you're going to put your real question in the alternative and kind of back calculate the mathematical opposite to state the null. You're going to decide on a significance level alpha. This is the amount of risk of rejecting a null hypothesis when it was actually true. And so this is usually a manager executive level decision. Usually you don't just decide this on your own, although for our class and our examples, we will be. We're going to compute the value of the test statistic, which is similar to getting a z-score, and then determine the p-value associated with that test statistic. And you're going to compare that p-value, which is a probability in a tail, to the amount of alpha that you are willing to accept. If it's less than the alpha, then that means it's very unlikely that the mean was where you thought it was, and the null, and you reject the null. If you reject the null, this is the only way to, this should have also said, accept the alternative. So this is the only way to accept what we originally see in our exploratory data analysis that we believe, this must be an A, is true. Otherwise, we do not reject the null. And then we always want to interpret the results of the hypothesis test. Right. So car insurance company is working on its rates and needs to know how many miles on average a car goes before it dies. The 2010 average was 185,000. In 2022, they obtained a sample of 200 cars with the miles at which they died. So here's our sample size, n equals 200. State the alternative hypothesis for this sample data. Get the alternative. State the concern with an inequality. Start with English. The average miles a car lasts before it dies increased since the 2010 average of 185,000. Identify the correct statement of this alternative hypothesis below. So you want to start with what the concern is, right? Because they're concerned if on average cars are lasting longer because they're providing insurance. So they put that, so we state it in plain English and then convert this plain English to math. So what you're doing is converting this English to math in this question. All right. So far we have covered for numerical data, not categorical, numerical, and one sample. We have two tests. We have the single mean test when we know this population standard deviation sigma. We know how to calculate that standard error. We know the distribution that applies and the Excel function to use. In the case where we have a t-test where we have an unknown sigma, this is much more the situation we're going to be in. If n is less than 30, the sample size is less than 30, we need to know that the data is normally distributed and there's no outliers. If the sample size is greater than or equal to 30, we can assume we're close to normally distributed and that there are no but we also need that there not be any outliers. So that's a second requirement. The standard error is almost the same. It's s divided by the square root n. This test statistic will follow the student's t distribution and with the degrees of freedom n minus 1. If you're in this situation, and I will be showing you some examples in Excel, and they are in videos on Brightspace, we can use built-in test hypothesis testing in Excel. We have the t, or we can use a distribution. So in this, we have the t distribution as a test statistic, the degrees of freedom, true. This is if it's a left-tailed test. We add a dot RT if it's a right-tailed test to give us the p-value. And if it's a two-tailed test, it's the t distribution 2t. Again, the slight difference is if you're getting just a left-tailed test, you have to add the word true. If it's a right-tailed test, it's assumed true, and if it's a two-tailed test, it's assumed true. So there's only the test statistics and the degrees of freedom that you would have to input here. Okay, and that's it for hypothesis testing with numerical data on one sample.